Hello everyone, I am Ratan Sharkar, one of your TA. So Abhishek Thakur and I will explain about this experiment. So first I will discuss the introduction and the how to make the table of this experiment and calculation part. And after that, Abhishek Thakur will explain how to perform the experiment. So let's go. What is Helmholtz coil? So Helmholtz coil is there is two coaxial coil, each having number of turns is capital N, and both coil are identical, okay, and they are placed at a distance capital R equal to the radius. So due to that, what happened? So before going to this Helmholtz coil, let's discuss a little about single circular coil. For single circular coil, what is the magnetic field at a distance x in the axis? So that is, this is the formula, okay, mu naught Ni by 2. So x is in denominator, so if you put x equals to 0, then B will become maximum. So at center the magnetic field is maximum. So in this case, if you plot what is the variation of magnetic field, so for single coil, at center the magnetic field is maximum, and as you go far from the center, this magnetic field will decrease in both sides. So in this coil also, at center magnetic field is maximum and both sides it will decrease. So in between them, the magnetic field is a combination of these two, and that will be like that, okay. So around center, around the midpoint, this variation of magnetic field is almost constant. So the reason behind this keeping them at a distance r is to make this constant magnetic field, okay. So in this experiment, our motive is to measure this uniform magnetic field, okay, of these two coil. So these are, so what is B here, okay. So these are motive in this experiment, okay. Now what is the value of magnetic field here, okay? What is the working formula? So working formula is so first working formula, V equals to 8 by 5 root 5 mu naught Ni by R. So write it as a IH, okay, Helmholtz current. So write it as a Helmholtz current, okay. So this first formula, using this formula you can calculate theoretically what is the value of magnetic field here, and also this is for table 1, okay. I will discuss later what is contains in table 1. So now what happened if we put some current carrying loop here in between these two coil? What happened? So suppose this contains IL current, okay. So we place some loop here, current carrying loop. So you know that when you place some current carrying loop into a magnetic field, what happens? This loop will experience torque, and due to torque it will rotate into the magnetic field. So what is the formula of torque? So formula of torque is M cross P, okay. M means magnetic moment. So what is the magnitude? MB sin alpha. So M means magnetic moment, current into area. So if this loop contains number of turns is 3, then so in some experimental setup number of turns is 2, some setup n equals to 3. So it depends. So in general n pi, so this circular loop, n pi r square area into loop current IL, okay, into B sin alpha. So this is the formula of torque, okay. So in this experiment we have total 3 table. In table 1, using Hall probe and Gauss meter, we can measure the magnetic field here. What is the magnetic field? So this will be table 1, but in table 2 we will use this torque method, okay. So there is a torsion dynamometer. Using this torsion dynamometer we can get the value of torque here. Okay, force, what is the force applied or torque in this coil. So another two table is, so how can we vary this torque? Okay, so we can vary this torque by varying. So there is so many parameter, but in that particular experiment we will vary just IL and alpha. Okay, alpha. So in table 2 we will vary IL and keeping all other parameter constant. We'll just note down what is the how torque will vary. So in table 2 we'll torque versus IL. So we'll vary IL and we'll check how this torque will change. Okay, so this will be our table 2. In table 3 we will change alpha and we'll check how this torque will change. Okay, so we'll torque versus sine alpha. So we'll see this variation. Okay, if you plot here, okay, torque versus IL, then it will become, from equation it will become a straight line passing through the origin. Here also if you plot torque versus sine alpha, then it will also be straight line passing through origin. Okay, and there you can get some slope s1 and s2. Okay, so using this slope and using this formula you can get this, from this formula you can get b1. What is the value of b1? So there will be slope by n pi r square sine alpha. That will be our b1. And similarly from this graph you can calculate what is b2. Okay, there will be s2 by n pi r square, from here n pi r square, then IL. Okay, so using this method we can calculate experimentally what is b1 b2, and we will take the what is the average value of b average. Okay, equals to b1 plus b2 by 2. Okay, so I am explaining again. So in that experiment there is total 3 table. In first table we will calculate using Hall probe and Gauss meter. Using this Hall probe and Gauss meter we can measure the value, what is the value of magnetic field here, directly inserting this Hall probe in between these two coils. And in table 2 we will using the torque method of torsion dynamometer we can vary current and just note down this torque value. In table 3 we will vary this sine alpha and note down this how torque will change, and we will plot this torque versus IL and torque versus sine alpha, and we will get this b1 and b2 from the graph, and we will take b average. Okay, so these are our basic idea of this experiment. This is the table 1. So table 1 will using the Hall probe and Gauss meter we can measure the magnetic field by inserting Hall probe into a Helmholtz coil. So for 2 ampere and 3 ampere we can measure experimentally what is the value of this, and also using this formula we can calculate this theoretical value of magnetic field. And each table minimum you have to show one calculation properly. Okay, so you have to show that. So this for 3 ampere, this theoretical value will you have to use further for further calculation. Okay, for theoretical calculation in table 2 and table 3. So we call it as a BT. Okay, we will use this further. So this is table 1. So this is table 2. In table 2 this angle is constant as 30 degree. Helmholtz current also constant as 3 ampere, and this is another information you have to write here. And for loop current we will just, in table 2 we will just vary this loop current, and first from torsion dynamometer we get this force value, and if you multiply with this half length of this torsion dynamometer then we will get this torque, experimental torque value. As for 2, 3, 4, 5 ampere we have to you have to measure this value. And also there is a theoretical calculation, and for theoretical calculation there is a B value, and what is BT here we will get from table 1. Okay, and this BT you have to use here for theoretical calculation. So this is the table 2, and this is table 3, and table 3 will vary alpha, okay, sin alpha. So keeping IL constant, loop current constant as a 4 ampere, and Helmholtz current is 3 ampere, and also BT here is right. So here 15, 30, 45, 60 for this 4 angle you have to measure this. Okay, what is the force value, and this is the experimental torque, and also you have to calculate this theoretical torque using this formula, and you have to show minimum one calculation. Okay, you have to show minimum one calculation, okay, properly. So using table 2 and table 3 you will now you have to plot the graph, okay, experimental graph. So from table 2 if you plot graph, then graph will be torque versus IL. Okay, so torque is directly proportional to IL, so the graph will be a straight line passing through the origin. So it is must, okay, it will be passing through the origin, and you get some slope here, okay, S1. Similarly from table 3 if you plot torque versus sin alpha, so here sin alpha torque is directly proportional to sin alpha, and here also this is a straight line passing through the origin, and you have to take the average line. So here you will get some slope S2. So from slope you can calculate this using this formula. You can calculate what is B1 from table 2 and what is B2 from table 3. So B1 is S1 by n pi r square sin alpha. So this is B1, and B2 is slope by n pi r square IL. Okay, now take average of these two, B1 plus B2 by 2. So this is the method. Okay, now error calculation. So there is two type of error. One is one first error is how your experimental value is deviated from the theoretical value. Okay, BT. So BT is, you will get BT from table 1. So magnetic field, theoretical magnetic field for 3 ampere Helmholtz current. So you have to take magnitude. So this from graph 1 and this is from graph 2. Okay, B1, B2. And what will be the instrumental error? So instrumental error, there is a two type of instrumental error. One error is due to this force measurement, and there is due to this angle measurement. And here you have to use the information from table 2. Okay, so using table 2, so where force is minimum, you have to use this information. What is the force, what is delta F, what is alpha. Okay, and here a value of delta alpha is pi by 180. You have to use this one. And from here suppose this k, this equal to k, then delta B equal to B average into k. Okay, we will get delta B from here. So after that final result, so so you have to write proper unit. So what will be the final B? So there will be B average plus minus this delta V. Okay, with proper unit. Okay, this is the method. So after that Abhishek Thakur will explain the experimental procedure, so how to do the experiment.
Hello everyone, my name is Abhishek Thakur and I am going to be your TA for this semester Helmholtz Coil. There will be other TAs also, but I am going to explain about this setup and the working principle of the Helmholtz Coil. So basically we have two coils, and through this coil the magnetic field is generated at the center. Now if you look at it, there the setup is quite rigid and it is fixed. It is because the radius of this coil is equivalent to the distance between them. What it does is that it produces a uniform magnetic field at the center. which we are going to use and calculate the magnetic field that is produced at the center through the help of this coil. So let us now look at the equipments that are being used in the experiment. So this is Hall probe, this whole setup. So basically the probe is the upper part, and we have power supply, and we have a Gauss meter. We have this Helmholtz coil. These large coils are Helmholtz coil, and this smaller coil you are seeing is the small coil that we will use to see the magnetic field. Now, to the first step of the experiment is to, now we have to use this probe to see the magnetic field here. What you will do is that firstly we will make this to 90 degree, and we are going to insert this here, somewhere here, and we have also been provided with the box with the wires. So we will use this wires to connect it. So you see there are 3 wires here. So you have 2 red wires and 1 blue wire, and you, if you see here, that there are in the power supply there are 2 colors, one is black and one is red. So you also have to follow the color coding. So the red one goes with the red and the black one goes with the blue. So let us connect and see how the connection is. So you connect with the red to 2 or 1, and then you connect this 2 to this 2. So and you have this now blue wire, which you are going to connect with this black, and then you connect this blue wire to the other source, which is one at the back side. So you connect this with this blue. So this one is your source, and 2 you are using to connect these 2. So once this setup is done, you turn this on, and you, there is, this is voltage knob and this is current knob. So you make this voltage knob to maximum, because you want to use the constant current mode, and you have to, so for this, so for the table 1 you have to use 2 values of the current, which is 2 ampere and 3 amperes. So we will set this current, we will set this current to 2 ampere initially, and you also see this Gauss meter which is kept here. The Hall probe is also changing the value. So if you fix it to 2 ampere, uh, yeah, so you see the value is here, this 15 point something. So you can move this probe little bit around, don't make an angle like this, you can move it a little bit around. And also this thing that you are seeing here, this black thing, should be perpendicular to this line. So your, this black thing that you are seeing is the Hall probe, and it should be perpendicular to this plane. So basically if you have this plane, it should be perpendicular to this right now. And if you look now, the value is around 15.6, which is a true value of this magnetic field. But if you will turn this to some angle, then you see the value is dropping. So it should be parallel, which will be given to you. But in case if it is not, this should be the case. Now once you set the value, you do the same thing with the 3 ampere current. So now the reading is 15.7 or 15.6 Gauss. This is in Gauss. You take, you can increase the current to 3 ampere for your next data point, and you note the reading, whichever reading is here. Use this anymore, so you can keep this aside. You have to use this equipment and this coil. So first thing that you have to do is that make it to 0. So how do you know it will be 0? The first thing will be this coil, the small coil will be parallel to this black rectangular coil. And if you still have a doubt, you can see at the bottom lines. So these lines that you are seeing will end after this bottom lines, and both on both sides it will end there. So it will be parallel to this. This will be your 0 degree. Now you have to also make this rod balance. So to make this rod balance, you have to make sure this rod is passing through this white region. So you have to make sure that it passes through that. So right now it seems like it is balanced. So now once it is done, you have to now see whether these three coils are parallel to each other or not. So the best way is to look at from this side and see whether these three are parallel or not. If it is not, then you make it parallel by rotating it a little bit. And also the distance of this coil from these two should be approximately equivalent. So this distance and this distance should be equivalent. So now once you are done with this setup, you have balanced this thing. So these are connected to the coil. You see, this is connected to the coil. So now you will use this equipment, these wires, to connect again using the color code. So color coding is important, remember. So you connect the black with the blue and you connect the red with the red. Now it is connected. And for the table number 2, you have to fix this angle to 30 degree. So how do you fix it? So at the bottom lines, the two consecutive lines have the angle of 30 degree, and above the two consecutive lines, so these two lines have the angle of 45 degree from here to here, and these two lines at the bottom from here to here has an angle of 30 degree. So to set it to 30 degree, you can go either clockwise or anti-clockwise. I am going anti-clockwise. So now this is at 30 degree. So once this is fixed, you again do the balancing of the above rod. So because since you are touching it directly, you have to make sure the rod is balanced or not. And so you balance it like this. And whenever you are changing the angle, make sure you keep your one hand here at the edge of this white region, and then you change this angle thing. Otherwise, what happen if you use both the hand, then there might be a chance that this silver wire that you are seeing can be broken easily, because earlier this has happened. So this is a precaution that you should remember. You don't use both your hand here, you keep your hand one here, and then you change the angle. So once you are done with this, you have changed the angle, you have fixed the balancing thing. So for that you have to use this lower knob. Once all this setup is done, you have to turn on this current which is connected to the smaller coil, and the Helmholtz coil current will be fixed, which will be 3 ampere while doing all the experiments. So we turn it on. Again you go to the maximum voltage, so you make the voltage knob to maximum, so that your reading is in constant current mode. So on all those things, your reading should be in constant current mode. So your first data will be for 2 ampere. So in this table you have data for 2, 3, 4 and 5. So you see, as soon as I have put it 2, there is some deflection. So earlier this was at the middle, now there is some deflection. So to see what the deflection is, you have to use upper knob to get the reading of the force. So this is torsional dynamometer, and this will give you a unit of force in millinewtons. So I am rotating in the opposite direction of the turn and seeing when it will get balanced. So it seems like it has balanced now. So right now I think it is balanced, it is passing through this white region, and you come and you see what the reading is here. So you see the reading is around 7, so it's 7 millinewtons, 0.7 millinewtons, so yeah, 0.7 millinewtons. And once you are done with this, to go to the second reading, it's important step, remember, you again turn this knob to 0. So it is important because this small coil can heat up easily and can then fall. So you turn this knob to 0. If you directly turn it off, the instrument may get damaged. So you turn it off, and then you make this to again to 0. And ideally this should not been affected, but since you are directly touching the table, you are touching the equipment, so it might get little bit out of the center. So you fix it again if it is not balanced. So once you see that it is fixed, for the next reading, that is 3 amperes, you again go to the 3 amperes. So you again go to the maximum voltage, and you then go from 2 to 3 amperes. uh, so I will show you only 2 data of this, then we will move on to the next table. Okay, so 3 ampere, and there is again deflection. Now you can see the deflection is more as than the previous one. Now you go back, you move this thing to balance and see where it is getting balanced. So you have to make sure you do it very quietly, do not disturb anything, otherwise there will be another unnecessary disturbance and unnecessary deflection. So once you are done with this, you see the reading is around 1.2. So it's a 1.2 reading, and this is in millinewtons, so 1.2 millinewtons. So for the next table, so you have to do all this data in such a way only. So as you have seen in the table 2, we were changing the current passing through this coil and we were keeping the angle constant. In the table 3, we will do the opposite. We will change the angle of this coil and we will keep the current passing through this coil constant, which will be at 4 amperes. Now how do one change the angle? So in this table you will use 15, 20, 15, 30, 45 and 60 degree, but there are no 15 degree mark here. So you have to use some technique. So basically you know that the angle between this and this smaller lines are 30 degree, the bottom one. So for going to the 15, you go just halfway. This will be your 15 degree. So let's say I have selected the 15 degree here, and then I have to balance it again, because every time you will touch the equipment it might disbalance it. So you again balance it. Once you balance it and this is at 15 degree, then only you change the current of this smaller coil to 4 ampere, which will be fixed throughout. So if you will look here, so you will change the current to 4 ampere, and you see there is this deflection happening. So earlier it was like balanced, now there is deflection. To again measure this deflection, you use this upper knob and then you move it. So it is around 0.9 millinewtons. And important, now once you get the data, the important step, it's a very important step, otherwise you won't be able to do the experiment further, is that you turn this knob to 0 quickly. So you turn this off, because this can easily get heat up, and you know what your reading is. So after doing this, you note down your reading and everything, and then you move on to the next. But make sure once you know the reading, you turn this thing off, otherwise it can heat up, it can fall down also. So to do the next reading, you again go to 0, but this time you have to change the angle. So again, well, how do you change the angle? You fix your one arm here, so your first finger and your thumb goes here in this white bar, and your angle will be changed to only one hand. So now it is 30 degrees, so 15 more, so this is your 30 degree. But now what happened, you are touching the equipment every time to change the angle, so every time you have to balance it before turning the current on. So if you look at the upper side, you have to balance it again. If it is balanced, then fine, and then only you turn on the current. So I'm not showing you this data, is a similar repetition, and that is the last thing that you do in the experiment, and then you have to do calculation using all those.